We live in the atomic age. Born in wartime, the atom has grown in peace to deliver unlimited power and unforeseen tools for medicine, industry, and research. No one can say just when the atomic age began. A long series of discoveries and experiments have made it possible. Each a step in the progression which has brought mankind's greatest opportunities and problems. This is the story of one memorable experiment and the scientists who were involved. The persons you see in this film, the voices you hear, are real. These are the people who opened the atomic age. And this is one experiment. The story of CP1, the day tomorrow began. It is December 2, 1942, the University of Chicago, birthplace of the atomic age. Here, behind the vine-covered walls of an almost abandoned football field, the government has already begun work on the most important device in modern history. Never before, and perhaps never again, will a single effort so profoundly affect the future of mankind. Here in this unimpressive building are gathered part of the elite corps of world scientists who are building the bomb. From every part of the world they've come since 1939 to join forces with American scientists. Never has such an array of scientific talent been devoted to a single problem. For in Europe, a desperate battle rages, and the Third Reich threatens to overwhelm the world. Among the first to feel the effects of the Nazi regime and understand its threat were the Jewish scientists. One by one, they left Europe for Britain, Canada, and most of all, the United States. With them came Italian Nobel Prize winner Enrico Fermi, whose wife was Jewish. Fermi was an unusual person. He combined experimental skill with theoretical talent and intense personal drive. Swimming, mountain climbing, skiing, he was always eager for a new challenge. Only a few days after the Fermis, there arrived in New York the most famous nuclear scientist of the time, Niels Bohr, the father of atomic theory. Almost everyone in the field had studied or worked with Bohr. Together with Professor John Wheeler at Princeton University, he developed the first theory of fission and debated the possibility of making the bomb.
I particularly remember the room down the hall where he was telling us, no, the bomb will not be possible. In principle, you could separate uranium-235 and make a bomb, but in fact, to do it would take the whole energies of a complete nation. Of course, he was only too right. It took the efforts of 3 nations to build it.
At Columbia University, Fermi was joined by another prominent physicist, Leo Szilard. Brilliant and volatile, Szilard was almost the antithesis of Fermi. He never lectured, never kept a schedule. A brilliant mind connected to a pair of hands that were never soiled in a laboratory. As the atomic fraternity collected, American scientists were made keenly aware of the German threat. James Conant, president of Harvard, and Vannevar Bush, president of the Carnegie Institution, were already organizing government support for scientific research. To the theoreticians at Princeton and Columbia universities were added the formidable talents of men like Arthur Compton, chairman of the physics department at the University of Chicago, and Ernest Lawrence, director of the University of California Radiation Laboratory and inventor of the cyclotron. Here was an American breed of scientists experienced in the construction of impressive hardware, conscious of world politics, and determined to enlist government support. By the end of 1939, 2 years before most Americans would become seriously involved, they had already organized a coordinated program to investigate atomic energy and had imposed a voluntary program of secrecy.
They started talking of the possibility of a chain reaction. Enrico explained it to me, and shortly after that, they stopped talking about it. They imposed secrecy on themselves, and then I didn't hear anything for years until the Smythe report.
Thus began the race to unlock the power of the atom, to harness it, to build the bomb. And just what is this phenomenon? What is atomic energy? All the universe is made of atoms, big ones, little ones, each a cloud of electrons around a little bundle of matter called the nucleus. Every atom is built this way, but in uranium, a few of the atoms are different. They are U-235. The energy in a few pounds of U-235 is equivalent to hundreds of thousands of tons of dynamite. If we could separate the U-235, the results would be fantastic. A bomb, a single bomb, powerful enough to destroy most cities. A bomb big enough to end the war with a single blow. In natural uranium, there is very little U-235. There is no way to make a bomb with natural uranium. But if we make a big enough block of uranium, so enough U-235 will be present, it should be possible to start a chain reaction and for the first time release atomic energy. Convinced that this was possible, Fermi and Szilard undertook to build such a device. In the meantime, at Berkeley, a team working under Lawrence had made a vital discovery. Using the cyclotron, future Nobel Prize winner Glenn Seaborg produced a submicroscopic speck of an entirely new element, plutonium. From incredibly small samples, it was possible to determine that here was a new man-made element which could substitute for U-235. The discovery made the Fermi-Szilard experiment more important than ever. If successful, the chain reaction could produce plutonium in unlimited quantities. Furthermore, U-235 was almost impossible to separate from natural uranium. But plutonium could be separated chemically. Here was the ultimate material to make the bomb.
The sample that was isolated as a result of bombarding these hundreds of pounds of uranium with neutrons at Berkeley and St. Louis was finally isolated in pure enough form to weigh a few micrograms by a special balance in which a quartz fiber is suspended at one end and comes out with a weighing pan hanging from that end, and then the sample put on that weighing pan depressed the quartz fiber, and the amount that the quartz fiber went down could be calibrated to correspond to the weight of the sample. And using that, the first sample of plutonium was found to weigh 2.77 micrograms.
This was an absolutely fantastic idea, not merely to make a bomb, but to make it out of an element that had never existed before, and to manufacture this new element. This idea of synthesis was so preposterous that you can say, how was anybody mad enough to think it could be carried through as it was?
So this is the problem. Make a chain reaction to make plutonium, to make a bomb, to end the war. In Columbia, in Princeton, in Chicago, the plan is set. To make a chain reaction, we must suspend lumps of uranium within a nuclear catalyst called a moderator. Heavy water would be the best moderator, but there is none in the United States. And perhaps we are already too late. In Germany, other physicists have a year head start. In Czechoslovakia, they acquire a major supply of uranium ore. And in Norway, they acquire the world's only significant source of heavy water. The combination was ominous. While the British set out to destroy the Norwegian plant, we searched desperately for a substitute. At Columbia, Fermi and Szilard, Anderson and Zinn make the first tentative tests of a new moderator material, graphite. A 4-inch square bar of filthy, dirty, slippery carbon, good for pencils, good for making arc lamps, good for oiling locks, and now good for splitting atoms. Cut the long rods into blocks, drill them with holes, and fill the holes with uranium. Then take the bricks and build a pile. The result? A graphite cake filled with uranium raisins. Is it really this easy? Well, no. There really isn't any uranium metal to speak of. In the whole United States, there is less than a couple of ounces. Not enough uranium, not enough graphite. But there is enough to assemble about an 8-foot cube. And from this, we can take some measurements. But the uranium is not good enough. The graphite is not pure enough. Over and over, small piles are assembled, always testing newer and purer materials. About this time, British scientists reached a dramatic conclusion. They estimated that as little as 20 pounds of U-235 could make a bomb. Conant and Bush were convinced. They launched an all-out effort to produce the bomb only one day before Pearl Harbor. Four parallel crash programs were begun. 3 concentrated on techniques to separate U-235. The fourth, the plutonium project, was placed under the supervision of Nobel laureate Arthur Compton. No longer was plutonium production a laboratory experiment. Now it was a military program.
I met Dr. Compton at that time, and of course, like everyone who met Dr. Compton, you could not help but be impressed by his enthusiasm and his earnestness and his complete confidence in success. I spent the morning going around the laboratory, and after considerable discussions with Dr. Compton, I was impressed with the idea that they had of attacking their problem on all sorts of different directions and not arriving at a decision. For example, they had 5 different methods that they were talking about for cooling the pile. Now, it just wasn't practical from a management standpoint and engineering standpoint, as well as a research angle, to proceed on 5 different things when there wasn't any advantage to be gained from it.
Within weeks, Compton's crash program to develop a plutonium-producing pile had committed over $1 million. Although no one had yet achieved a chain reaction, he laid out a timetable for completion of the project. By January 1943, to achieve the first chain reaction. By January 1944, to separate the first plutonium. By January 1945, to deliver the first bomb. It seemed certain by now that sufficiently pure materials would sustain a chain reaction. But it was not at all clear whether such materials could be produced. The most minute impurity could effectively block any reaction. There was only a single producer of large quantities of graphite, the National Carbon Company. And in Canada, the only significant uranium mine in the Western Hemisphere was being activated to produce uranium in large quantities. Until now, uranium had been only a scientific curiosity, a metal powder which occasionally burst into flames spontaneously. At Iowa State University, Frank Spedding, a chemist who had worked with similar materials, developed a new technique for producing the metal. Into containers was loaded a mixture of calcium and uranium salt. When ignited, the reaction produced a heavy ingot of substantially pure uranium.
There was a great deal of curiosity on the campus as to what we were doing, particularly as once in a while one of our retorts would blow up, and with the magnesium, which is what you use in flash powder, it would light up the whole building, and it gave a illusion. The light was so bright that the building swelled up and then sunk back. And the college press office was right across the street from this building, so naturally their curiosity was very great, but nobody would talk, so they didn't know what was going on.
Now Compton was sure the pile would work. Rather than wait for an actual demonstration, he recommended building a plutonium plant immediately.
And I told Compton that the only one that I knew of that could do the job was DuPont. And I talked to the DuPont people, and it was arranged. Finally, they agreed that they would do the job.
Well, I must say that this whole field was so new to us and so strange that we weren't sure whether these people were crazy or whether they weren't. It was completely unprecedented. The only thing we felt we could add to it, actually, was our knowledge and experience in designing and operating plants of great substance and great magnitude. So that we had been impressed with the enormous importance of this venture in terms of winning the war. Furthermore, we recognized this was a potential engine of great destructive power, and we didn't want to make any money out of it. So we decided, as a matter of patriotism, if you want to use that somewhat hackneyed word, that we should devote our talents to the service of our government in a critical time. We should devote our talents without trying to earn a fee, small or substantial, out of it.
November, and the pile begins. Not another test this time, but a full-scale attempt to start a chain reaction. This will be the 31st pile, bigger and with better materials. If the new pile is big enough, it ought to go. But because there is so little material, so variable in quality, we must be miserly. Make every bit of uranium count. No rectangular pile this time. We need the most efficient pattern for our small supply of material. Round. In the middle, where it will do the most good, we will put the uranium metal. Around this, we will put the weaker uranium oxide, always with the best material toward the center and the poorer toward the outside. And of course, as always, the material must be formed in lumps, and between these, the graphite moderator. Under and around the graphite is wood to carry the load and fill in the corners of the big block. And what if there isn't quite enough material? Or what if the material isn't quite good enough? Then what? We can do one last thing. We can take out the air between the bricks. So, just in case, we order from Goodyear a square balloon, just the right size to fit around the pile of carbon blocks. And if we must, we'll pump out the air. As fast as material arrives, it is sawed and planed, drilled and turned and pressed, and stacked in the ever-growing pile. Here are actual photographs taken as the pile progressed, layer on layer of graphite bricks and uranium eggs. But size is not enough, because if it works, this pile, Chicago pile number 1, will need to be controlled. Here's how. Into the pile, we will add rods of cadmium, which soak up neutrons. As long as these rods are in the pile, there can be no reaction. But pull them out, push them in. These are the control rods which will turn it on and turn it off. There are 3 sets. First, a set of motor-driven rods, controlled from the balcony. These will be used for a coarse control of the reaction. Second, one additional rod for fine control. This will be pulled out by hand. Last, running right through the center of the pile, is an emergency rod. In case of trouble, this emergency rod will be pulled into the pile by a rope attached to a heavy weight. Day by day, the pile grows higher. Week after week, the crews work at making the graphite bricks and pressing the lumps of uranium oxide. This is not a little experiment. 400 tons of graphite, 50 tons of uranium, 40,000 bricks to be sawed and planed and drilled and stacked, 22,000 uranium slugs to press and place.
Graphite was being received from several manufacturers, and this material, when it arrived, was in rather unusable form because as it was made, it had surface roughness and actually a little distortion in the bars of graphite, which didn't permit its direct use. So these bars had to be machined, and we set up a machining facility. The word facility is a little bit grand for what we had. We put some machines and some ventilation into a room in the squash court and proceeded to square up the bars and cut them to the right lengths.
My objective was always to equal or better the performance of Zinn during the day. So my group always put on the same number or one more layer, and then we went home. So it wasn't really a 24-hour shift, but it was more like 16 or 18 hours or something like that.
Now, Wally Zinn wouldn't let me work at the squash court because, you see, everybody wore overalls and goggles and a mask against the dust, so everyone looked alike, and a miner's cap, you know, a regular striped blue ticking workman's cap. So everyone looked alike, and he said in case he had to say nasty words to somebody, he didn't want it to be a girl. So I was excluded from the actual construction, although I was in and out every day with calibrations and measuring the growing neutron flux of the reactor as it added layer by layer. It was a very hard driving operation. There were people cutting the graphite, carrying it, stacking it, drilling it, and of course there was graphite dust everywhere. Everything was black.
I remember one night when we were pushing these things, we used just ordinary woodworking tools, you see, and we were pushing these through the shop, through the planer. And here was Enrico Fermi, stripped to the waist, pushing these graphite blocks through the shaper. Just glistened, absolutely black, clear to his waist. Well, it was just throwing graphite dust in every direction, you know. He could have had a part in Othello that would have made him internationally recognized as one of the artistes of all time. Just one could have had a color photograph of that, it would have been worth many fortunes.
December 2, a cold winter day, and under the stands the steam lines have quit working. In the beastly cold, with the snow creaking underfoot, the scientists gather. And now the test begins. The first control rods are pulled out, and the emergency rod is tied in place. Step by step, inch by inch, Fermi calls for the control rod to be withdrawn. Bit by bit, the rod is pulled, and each time the intensity rises. Each time, Fermi predicts the level where the rise will stop, closer and closer to the point where it will not stop. By the rail, Norm Hilbury stands ready with a hatchet to cut the line holding the emergency rod.
Quite frankly, it never occurred to me that the axe would really have to be swung, any more than I am sure it ever occurred to Al Graves and company that they would ever throw these damn bottles down because they saw some glow.
Above the pile, just in case, are bottles of cadmium salt solution, ready to flood the pile and stop the reaction in case of trouble.
The last words Fermi said to him was, now if this is the final emergency, if the thing gets away from us, you're to break this. But he said, I want you to know that you're to watch me, and if I drop dead, then you're to break it. If I'm alive, I'll use a sledgehammer on you.